All right, thank you. Thanks for the invitation. It's a pleasure to virtually be here. I wish I could be here in person. So I'm going to talk, this is going to be a mostly expository talk. So it's not, there's going to be a small amount of, new stuff at the end, but it's mostly supposed to be a gentle introduction to stable envelopes, give some context for some of the other talks today and afterwards. So, all right. So the basic idea just the real basic cartoon, you have a group, or really a torus, the abelian group. So if you start again, which is acting on some space X. Usually X will be symplectic, although that's not strictly necessary. And you want to construct a map from the equivariant cohomology of X, or the fixed points of X, rather, to the equivariant cohomology of the whole space, satisfying some nice properties. So that's the goal. And note that we already know some, let's say, maps going the other direction. So we have restriction. Cohomology gives a map in the other direction. And this is an isomorphism after inverting some parameters. Some guys inside the equivariant cohomology of a point. So this is the Atiabat localization formula. Actually, honestly, I should be careful about attributions because I forgot to check that one before the talk. So anyways, so we have an isomorphism after localizing some equivariant parameters. And now we're trying to construct the map in the opposite direction, which is just going to be defined on the integral equivariant cohomology, so without localizing parameters. Okay, so it's not the inverse of the restriction map. Okay. So you can do this in cohomology, but actually we're going to do it in K-theory first. So and then in elliptic cohomology. And this theory is basically due to Malik and Kunkov. So, okay, so we need a few preliminary definitions before we can define our map. So given some class, now in the equivariant K-theory of X, and some, let's say, fixed point, which we're going to suppose for simplicity is isolated. When you restrict your class to this fixed point, this is just an element of the representation ring of your torus. So you can write it as a sum of just characters of the torus with some integer coefficients. And we're going to define the degree in A of this restriction to be equal to, myself a little more space, equal to the convex hull of the mu that appear here. So convex hull where? So this is inside the so the dual of the Lie algebra. Yeah, say over R. So this is some notion of, I don't know how big your restriction is. It generalizes in a loose way the cohomological degree of restriction to, let's say, an equivariant cohomology class to a fixed point. So so we can order these degrees by containment. So the degrees of polytope, if one polytope is contained inside the other, well, then we say that the degree is smaller. So, okay, so we have a sort of a notion of degree, which is a substitute in K-theory for the cohomological degree in cohomology in this narrow context. Okay. So to define our K-theoretic stable envelopes, we fix some auxiliary data. So number one, so maybe I'll just recall the setting. So we have a torus A acting on X. This is a Hamiltonian torus. Action. And we are usually in a setting where A is a subtorus of a bigger non-Hamiltonian torus. So this is a non-Hamiltonian torus action. And so we're interested in the equivariant cohomology for the bigger torus, but a lot of our constructions will use the smaller torus only. So here you can make one more assumption on this. So let me move this up a little bit. On this bigger torus, which is that it's non-Hamiltonian, but it scales this symplectic form by a character. So that's if you like, you can imagine you have A as Hamiltonian and T is A times C star, or C star scales the symplectic structure. Okay, so back to our stable envelopes. So we need some auxiliary data to define them. The first most important piece of data is a co-character. So sigma map from C star into our Hamiltonian torus, which is generic in the sense that if you look at the subgroup of A generated by sigma, and you look at the fixed point set for the subgroup, it's equal to the fixed point set for the whole torus A, which is a priori much bigger. Sorry, much smaller. Okay. Actually, the construction will end up only depending on not on the co-character itself, but on the sort of vial chamber the co-character lies in. Let me not say any more. You can guess for yourself what that might mean. Second piece of data, which is not that important for us, and you can kind of forget about it for the rest of the talk, is choice of polarization. That means splitting of the tangent bundle of X into two dual halves, which I'm writing T half and T half check. So this splitting takes place inside the K theory of X. So you don't always have such a thing, of course, but if X comes to you, let's say, as a Nakashima quiver variety, hypertoric variety, those guys have natural polarizations. So they look a little bit like cotangent bundles. They inherit a polarization from the natural polarization of a cotangent bundle. And notice here the scaling character of the non-Hamiltonian torus makes an appearance. So this is sort of telling you that you have, let's say, T half is sort of the tangent directions, and dual is the cotangent directions. Okay, and then we have third piece of data is a slope, meaning a line bundle, equivariant line bundle. Actually, we don't want a literal line bundle, we want a fractional line bundle. And it should be strictly fractional in the sense that its degree, when you restrict to any rational curve joining two fixed points, should be non-integral. So CPW are two fixed points. So I should maybe say I'm going to more or less assume that we have isolated fixed points during this talk, just for simplicity. That's the first case you should think about. But a lot of what I say generalizes easily to more general fixed points. And again, as I've mentioned before, this is not my work. So this is an expository talk for the most part. Just another disclaimer. Now, okay, so those are three pieces of data: a co-character, a polarization, and a slope. Now, given this data, we can define a sort of an ordering on the fixed points of X. How do we do it? So the idea is more or less, we want to say two fixed points are, one fixed point is bigger than another if it's upstream from it with respect to the scaling of this action of this co-character. So more precisely, we have a fixed point P. we define the attracting manifold with respect to sigma p. So that's just all the x such that the limit as z goes to 0 is sigma zx is equal to p. So you could imagine, let's say, let me draw an example here. So if x is t star p1, potential bundle p1, which is sort of the smallest symplectic variety I can think of that will give you an interesting answer. Let me draw a little picture of it. So here's P1, here's 0, here's infinity. This is the conormal to infinity. Here's the conormal to 0. And we have some scaling action of sigma, right? So let's say as z moves around, you move in along these red lines. And so if we pick, let's say, infinity, what is its attracting set with respect to sigma. So okay, the arrows are pointing in the direction of the z tends to 0. Attracting set will look like this. It will be P1 minus a point, P1 minus 0. On the other hand, the attracting set of 0 is going to be the conormal bundle to 0. So we see that one of these guys is closed, the other is not. They're both Lagrangians inside X, which is automatic because we start with a Hamiltonian torus. And they kind of suggest an order relation among the fixed points where infinity will be bigger than 0 with respect to this order. Okay, maybe I'll stop here if there's any questions.
All good on our end.
Okay, great. So we define the full attracting locus of P to be not just its attracting cell, but also all of the sort of downstream attracting cells. So just in this example here, that would look like both of these guys. So that's the attracting cell of the full attracting locus of infinity. Of course, if you're familiar with Morse theory, this is in the same spirit, although it's all in a complex setting. Okay, now we can define the elliptic, the K-theoretic stable envelope. So the stable envelope with respect to the data of the co-character, the polarization, and the slope of a particular point P, think of as generating the equivariant K-theory of that point. So that's an element of the equivariant K-theory of X. And it's defined by some conditions. It's a unique class such that number one, it is supported on the attracting locus of P, on the full attracting locus. So it's some, loosely speaking, it's some sort of rank 1 sheaf on this attracting locus. Number two, sometimes I won't write all the auxiliary data, I'll just say stab P. If you restrict it to P, this is equal to a certain line bundle, which I won't write down, times the structure sheaf of the attracting locus. So what this is saying is it's a kind of a sort of normalization condition, I think. So if you are looking near, like in a neighborhood of the point P that you started with, the stable envelope is some determined, twist of the structure sheaf. So this is an explicit line bundle. I'm not writing it down because the formula looks a little intimidating at first. So don't want to get lost in the weeds. And the third condition, actually, sorry, not only that, but I should call it something L. So let me call it I'll just call it L hat. Okay, and the third condition, this is the key one. So this is what makes the whole machine work. So it's the degree condition. So if you pick a point which is not P, which is downslope from P, you can consider the degree of the stable envelope of P at that point Q. Restricted to that point Q. That's a polytope, and that should be strictly contained in the degree of stab Q, restricted to Q. Oops, I'm not sure what happened there.
Yeah,
I'll reshare my
didn't
screen.
Get any of the writing on that.
I will rejoin. So it's a stop share. Can you see my screen?
Yeah, that's a lot better.
What did you miss? Where should I?
Oh, we heard what you said, but we didn't see you writing 0.3 when you were writing it.
Okay, yeah. So 0.3 says that, so it's a degree condition. So here, P and Q are fixed points, and Q is smaller than P in this this ordering, and it's saying that one polytope is contained inside the other. Actually, so this needs to be corrected. So you tensor by a sort of a constant factor on each side, where this L is the slope line bundle. That was part of our data. Okay, so these factors of L here, they just translate the polytope by some amount, by some non-integer amount, remember, because these are fractional line bundles. And so it says that the given translate of this particular polytope is contained in this particular polytope. So, you know, in English, it's saying that the degree is kind of small and restricted to these downslope components. And the point is that there's kind of a unique way to extend this particular twist of the attracting sheaf in such a way that the degree upon restriction to downslope components remains small. Okay, so there are, I think now a number of proofs of the existence and uniqueness of such a thing. In various settings, to do Malik and Kunkov. Some of them use Daniel Schenfeld's thesis. Kunkov gives some later proofs of different flavor. I'm not going to go over them, but in some sense, the idea is inductive. So you start by saying, well, we have an attracting cell for our fixed point, and then you try and extend it fixed point by fixed point, while always respecting this condition here. Sure, you can always do that if your space is sufficiently nice. Okay. So, well, fine. So we've constructed some map. So what you get in the end is you get a map sigma t half L from the K-theory of your fixed locus to the K-theory of X. So what is this bodice? What is this good for? Well, first, it satisfies some nice basic properties. Analogous to the restriction map. So number one, so here we need isolated fixed points. For the statement to make sense in this form. So the different classes stab P for P ranging over the fixed locus is a basis of the equivariant cohomology after you localize some equivariant parameters. So you can think these are all, in some sense, Lagrangian classes. And so this gives you a nice sort of quote unquote Lagrangian basis for the equivariant K-theory. This is analogous to the usual equivariant localization phenomenon. But unlike with equivariant localization, there's an interesting integrality property here. You've constructed actual classes in KT of X, not in some localization of KT of X. It happen to be a basis once you localize. And the second property is an orthogonality property. This is also very important. So it basically says that stab P for our given choice of auxiliary data is orthogonal, or forms a dual basis to stab Q for the opposite choice of auxiliary data. So I leave it to you to guess what it means to take the opposite auxiliary data. So opposite co-character, opposite polarization, opposite slope. Okay. But so this maybe should convince you that this is kind of a cool map. But in a moment, I'm going to show that it has something to do with quasi-maps, hence the relationship to this conference. So we will see how STAB, stable basis, allows us to study quasi-map invariance. And this particular application, I'm sort of quoting from a paper of Agnagik and Akunkov on elliptic stable envelopes. So here we go. So to do that, we have to introduce the elliptic version of stable envelopes. So actually, both the K-theoretic and the elliptic version sort of are useful for studying quasi-map invariance. But the elliptic version is a bit of a mouthful. So if you've seen them for the first time, it's better to start with the K-theoretic. What I'm going to do is give a very, very hand-wavy description of the elliptic guys, but appeal to, let's say, the analogy with the K-theoretic ones. All right. So here's a very loosey-goosey primer on elliptic cohomology. And so here we'll be taking the elliptic cohomology of the same space X, and we will really be interested in the equivariant elliptic cohomology. And so the elliptic cohomology in general is some really complicated gadget, but we're going to use a sort of simple version of it. So we fix an elliptic curve. E, you can think of as just C star mod some one-dimensional subgroup generated by a number Q of size smaller than 1. And given, so more generally, I can associate to the same number Q some higher dimensional abelian varieties. So given a torus A, let's see, start at the N, we let EA be the quotient of this torus by the subgroup generated by Q to the various co-characters of A. So this is a rank and abelian variety. And maybe if you're an algebraic geometer, maybe this is not the most interesting abelian variety, but well, good enough for us. So given this data, the elliptic cohomology, so what is it? It's a functor, it's a covariant functor. I'll write it as L sub A that takes as input a scheme with an A action and produces a scheme. And which associates to the point this abelian variety EA. Of course, this doesn't define it uniquely. I'll give you some examples in a minute that give you some intuition for how this actually works. But just by analogy with K-theory, so K-theory takes an A scheme and returns a ring. Of course, I could take the spectrum of this ring and I'd get a covariant functor into schemes. And if I take the spectrum of the K-theory ring of a point, what do I get? I just get the torus that I started with. Okay, and so you can see that we've set ourselves up to get some sort of cohomology theory where wherever I saw a torus in equivalent K-theory, I now see an abelian variety. Here's an example of what this functor does. So if we take our scheme X to be just P1, acted on by C star. So, well, the elliptic cohomology of X is some scheme, and it has a natural map to the elliptic cohomology of a point because there's an A-equivariant map from X to a point. So what's this elliptic cohomology of a point? We know that that's just the elliptic curve that we started with. Let me draw it maybe somewhat non-standardly as a line. And the elliptic cohomology of X is going to be just two copies of this elliptic curve meeting at a point. Okay, and what does this picture, how do we come up with this picture? So this is E, this is E0, infinity. So basically the idea is you can think of it as an analog of the GKM description of equivariant cohomology. So each fixed point gives you a copy of your elliptic curve.
I think we've lost your writing again.
Oh, sorry about that. Can you see it?
Yeah, sorry. I was mistaken. You weren't writing when you were talking.
Oh. Well, that's just bad practice. So, you know, I have to write at least one thing per sentence. Okay, so all right, so here we have the two copies of our elliptic curve corresponding to the two fixed points. Infinity and 0. And if we look at, let's say, the fiber over a generic point here, we have two distinct points. So this fiber, call this epsilon, this fiber you should think of as the equivariant K-theory of the fixed. Sorry, so think of it as the equivariant K-theory of X, but where you specialize your equivariant parameters at epsilon, and that sort of canonically decomposes as a direct sum of equivariant K-theories corresponding to the fixed locus. On the other hand, if you pick the sort of identity or the unit inside the elliptic curve, this is more like just the ordinary K-theory of X. So it's this sort of nilpotent thing. Really here I should be talking about cohomology. But anyways, so, okay, so hopefully this gives you a picture for elliptic cohomology. It's pieced together out of the, let's say, equivariant K-theory or equivariant cohomology of your space, specialize the different parameters. And it looks like a bunch of abelian varieties glued together along abelian subvarieties. Okay. So elliptic stable envelopes. So if you look at the definition, again in Aganage-Kunkov, this is quite a mouthful. It's a little hard to process at first, but very roughly speaking, the idea is pretty straightforward. You again want some map from, well, let me say something wrong first. So maybe you might think it's a map from the elliptic homology of A fixed point set to the elliptic homology of the full space. Well, that's not right, because our we've sort of taken the spectrum of our ring. Functors going the other direction. So it should be something more like, functions on this space to functions on this space. But these spaces don't have a whole lot of functions because they're proper schemes. So really what we want is sections of line bundles on these spaces. So we're going to pick a certain line bundle here, and a certain line bundle here. And yeah, we're going to construct a kind of stable envelope map from sections on one guy to sections on the other. Even that is not fully accurate. So recall that the K-theoretic stable envelope depends on a slope. This is inside the Picard group. So our elliptic stable envelope will depend, so this dependence was discrete in the case of the K-theoretic stable envelope. So the elliptic stable envelope will depend continuously on a choice of parameter. So the elliptic stable envelope depends continuously on this parameter. Another way to put it is we're really looking at something like the elliptic homology of A times something like the Picard group of A. This is some lattice, usually, which you can turn into a abelian variety, parametrizes the fractional line bundles. This is the same thing for X. Okay. So in practice, for simple examples, such as T star P1, you can get away with a kind of an explicit, writing down explicitly what this is, and the answer is relatively straightforward. So, sorry, again, I forgot to specify a line bundle. Can write explicit formulas in terms of theta functions. So a section of some line bundle on the elliptic homology scheme, you can write the data functions. Okay, so I'm running out of time. I'm very much running out of time. 50 minutes past. So let me just say, we advertise an application to quasi-maps. This was sort of the original one. So there's a, so to speak, elliptic R matrix. Where you take stab P and you compose it with, sorry, not stab P, but just stab, composed with stab sigma prime inverse. So this goes from, let's say, the elliptic homology of the fixed point scheme to itself. Like this, possibly localized. And so you can express the monodromy of sort of quantum difference equations in terms so sort of satisfied by the vertex functions in terms of this elliptic R matrix. Okay, so yeah, so I am happy to discuss this some more after the talk, and also to say a little bit about my own work with Sushmita and Yao on these elliptic stable envelopes. But hopefully this was a sort of helpful intro to them for the next talks today. Thanks for your time.
Thanks, Michael. Let's thank him for his great talk. Are there any questions from the audience? We have one from Tudor.
Hi, Tudor.
Hey, Michael. Nice to be sort of on your side of the world. So it's a very tangential question. Are there any similar statements for categories of sheaves in terms of relating something like sheaves on fixed points to?
Yeah, so there's I think Daniel, who is he there? Is he physically in Bengaluru? He's not. Well, I think he's giving a talk later today, right?
Yes, yeah.
So him and Devesh and Andre, I'm not looking at GluCop, they have this project to categorify these stable envelopes. So you get a map from, coherent sheaves on the fixed point set to coherent sheaves on the full space. And lots of parts of this project are already done. I actually don't really know what the status is. Maybe they've proven everything, but you can ask him about it. But the basic idea is it's closely related to the stuff that Daniel did on magic windows and so forth. So kind of unique ways of extending coherent sheaves from an open set of a space to the full space.
Great, cool.
Sure.
Thanks. Any other questions?
I actually had a much more naive question. Why is there an inverse of this stab functor?
So there's not an inverse in ordinary, let's say, K-theory or whatever, but there is an inverse once you localize around parameters, because I claim, well, at least in K-theory, I claimed at the very beginning, the stable envelopes form a basis, right? Where did I claim that? It's here, got it. Yeah, so property 1 tells you that the stable envelope map, after you localize, is an isomorphism.
Right, okay.
And so, no, that's not, that's somehow, I've assumed that the fixed point set is isolated, and I'm making some niceness assumptions on X that I've not spelled out, but that's true in, let's say, for hypertoric varieties. And so then you can invert the map after localizing equivariant parameters.
Okay.
And maybe if you think about it, so the R matrix that you get by composing a stable envelope and an inverse of a different stable envelope is going to, so it's going to depend on these equivariant parameters. And because you've localized some equivariant parameters, there's a kind of meromorphic dependence, right? It's going to have some poles, which is something that it's familiar in theory of R matrices for loop groups, quantum loop groups, and so on. All right, thank you. Hope this wasn't too basic, but yeah, hopefully it should help some people with get a taste for what these stable envelopes are.